Let's get this party started. Okay, so getting started. Like I said, the first one is Linkerd E28 Updates. Oliver, what you got for me?
So 2.8, we're mostly focusing on getting the multi-cluster stuff into usable state. And so we've been blogging about that and getting a bunch of the kind of raw pieces in place. I think we might be more or less feature complete in this week's Edge, but we have a few more weeks of testing and doc writing and general cleanup to do around that feature before it gets ready for stable. So I'm hoping, probably mid to late May is when we'll get 2.8 out. And we're also in the middle of doing a bunch of 2.9 planning and moving some pieces forward for the next set of work too.
Yeah, that's a great update. In fact, I think in last week's Edge, you could run through the tutorial that we've got end to end. We landed the proxy features required to take that all together in last week's Edge. And so it should work, though. I will warn everyone, because of a certain person's changes to the dashboard, it's a little rough. Charles took care of that for me, though. Multi-cluster is definitely the big thing. For those who didn't kind of know what happened with 2.7.1, we just backported proxy changes. And so everything that's happened since 2.7 from a control plane perspective is going to be coming in 2.8. And so it's not just multi-cluster. So while that is our biggest focus, there's been a bunch of great PRs that have been merged since then, though. Now that I've made a big deal about that, I'm totally drawing a blank on what PRs we've landed for that. However, I did drop a link for what the service mirroring kind of write-up that I did, maybe, let's see, end of February at this point. Man, this year is moving fast, into chat. So you can take a look at that and jump into Linkerd Slack if anyone would like to go do an end-to-end on the multi-cluster. We've got it as a docs PR at the moment. Would absolutely love feedback, because we definitely need more testing on it to get it done.
And we've had a few people set it up and use it, right?
I am aware of 2 people who were successful after checking out the proxy dev builds. So It is 100% doable, and we've really been enjoying the extra testing and that kind of thing. Let's see. I need to be able to type and talk at the same time. Just a second here.
Well, what do you want to talk about? Maybe you can start the talking.
Well, I think that's all we've got on Linkerd 2.8, and so kind of the next thing would be start asking Eliza all the questions about what's going on in Linkerd proxy land. I think to start it off, we all know that the Linkerd proxy is written in Rust. Eliza, can you tell us a little bit about what's been happening in the Rust ecosystem over the last year and why it matters that we're having a conversation about the proxy changing?
So just a little background. My name is Eliza Wiseman. I'm a proxy maintainer. I work at Buoyant. I'm also on the core team for Tokyo, which is Rust's sort of preeminent async runtime, which is a project which Buoyant has invested pretty heavily in the ongoing maintenance of. So that's my background. What's currently going on is that the Rust ecosystem is sort of undergoing a really big fundamental change in the way that we write asynchronous code. And the main driving force behind that is that now a couple months ago, the Rust standard library stabilized a definition of the future trait, and the language stabilized async await syntax. Rust has had asynchronous programming for a long time before then. Linkerd has been an is totally asynchronous. It's been a asynchronous IO project since its beginning, but in the old days, we had a future trait, which is sort of a Rust trait is kind of like an interface in other languages, and it's sort of the core definition of here's an asynchronous computation, and it's the fundamental primitive that this ecosystem is built on. Oliver has something he wants to say, sorry.
Yeah, I think many of you are more likely to have seen this in the JavaScript ecosystem, right? And so
Sure, it's like promises.
And there's promises, and then they introduce the await and the async function stuff, and it's very similar to what's happening in the Rust ecosystem.
Yeah, and this is quite similar. So before you have async await syntax, you have to interact with these future types with combinators, right? So you say like future.and then whatever, right? And now we have async await syntax, which is language level syntactic sugar that lets you write sort of nice straight line code instead of this sort of code where you have all of these like closures and callbacks and maps and thens and so on. And getting that into the language required some changes. So what happens is that we now have this async await syntax, and when we use that syntax, the Rust compiler sort of generates all of the state machines and all of the like combinator driven code that you would write previously. But there had to be some sort of breaking changes to the definition of how futures work. And doing that has sort of triggered a huge set of breaking changes all across the async ecosystem, because it's sort of a fundamental, the fundamental building block of all async programming in Rust. And so because that changed, we have also all been taking the advantage of like the breaking changes necessary to support the async await syntax to also make all of the other sort of changes that we couldn't make because they would be Semver incompatible, they would break a lot of code. Well, you know, now's a good time to fix everything else that we've learned over the last several years of working with the original 0.1 version of the futures libraries. So
let's talk about this from the Tokyo perspective. And
yeah,
I'm making things up here at the moment. So Tokyo 0.1 had an API.
Yeah.
Because of async await, the Tokyo 0.1 API was going to have to change because it's going to move over from futures. And so because the API already had to change, y'all figured we might as well not just stop at changing the API a little bit, but actually update it significantly with all of the other updates that we wanted to do at the same time.
That's exactly right. All Rust libraries or Rust packages, the Rust name for them is crates, but you know, a crate is just a package. It's pretty widespread that really it's encoded in Rust package management system that we use semantic versioning to version these things, right? So you have like a major, minor, and patch version. And the minor version is things that you've added. The patch version is like small bug fixes, and the major version is every time you change an API in an incompatible way. And because Rust is a statically typed language, there are a lot of, you know, and it is a statically typed language with pretty rich type system, there are a lot of ways that you can change APIs that just mean any code that depends on this doesn't compile anymore. You've totally broken it. And that just doesn't work. You know, in a language like Python or a language even like Java, where you have things like variadic arguments, you can make changes to APIs and sometimes remove things or move things around in ways that are less breaking. But because of the semantics of the language, it's hard to make these sort of breaking changes. And the maintainers of all of these packages are generally very heavily committed to stability. Tokyo in particular is like a very foundational library. We like to call it Rust's async runtime. And what that means is that it's really providing a lot of things that most other languages have built into the language runtime. So like languages that have async await syntax, like JavaScript, Kotlin are good examples. They have some kind of runtime, right? In the case of JavaScript, it's the web browser or it's Node. And in the case of a language like Kotlin, it's the Java virtual machine. And there are a lot of services that you need to provide that kind of asynchronous IO. You need a reactor, which is the component that's looking for event notifications when like some IO happens. You need a way of running timers. You need a way of managing what asynchronous tasks or green threads, depending on what you call them, are running. And all of that stuff is like a big bundle of code that normally is in a language's runtime. And Rust has this kind of nice advantage of being a systems programming language. It has really low level control. And that means that a lot of this stuff that traditionally has to be built into the language and its environment is sort of a library that you can just say, I depend on this library. So because of that, like Tokyo is very fundamental. So many projects in Rust use it and use it really heavily that we have learned to be extremely sensitive for not breaking this stuff willy-nilly. It's been stable for a very long time. And because of that, we have this big backlog of like all of this stuff that we've really wanted to change. And we're taking advantage of this sort of breaking change we have to make to also change a lot of those things.
So in JavaScript, when async await happened, it was mostly transparent. Is the reason why that wasn't the case in Rust the type system?
Pretty much, yeah. I mean, so JavaScript is a dynamically typed language. Everything is nullable in JavaScript, right? So anything can be undefined. And it has a lot of properties that it has basically no static checks is the other thing. Not only is Rust statically typed, but the Rust compiler enforces a lot of stuff. JavaScript, you could argue whether or not JavaScript has compilers, right? But like at the core level, JavaScript is an interpreted language, right? So you take the program text in and it's executed by like V8 or whatever. And because of that, a lot of stuff happens at runtime. And, you know, that's a double-edged sword. One, these static languages tend to have significantly better performance properties because you're not figuring everything out at runtime. Set that aside. Two, you kind of have this advantage of you can use these static checks to enforce that you're actually writing correct code. That in a dynamic language, you have to do a lot of checking the correctness of your code with testing, with assertions, with the stuff that has to be evaluated at runtime. In a more static language, you can rely on static guarantees. But the double-edged sword is that it's very easy to paper over incompatibilities at runtime, right? Like at runtime, you can run arbitrary, sorry, my cat is, you can run arbitrary Turing complete, you know, executable programs. You can do a lot of stuff in an arbitrary Turing complete executable program that you can't really do statically. So it's very easy to say, oh, these APIs are incompatible. Well, if this is called with the old version of the API, we're just going to have a bunch of if statements that sort of paper over. And there's not this sort of like, there's a difference between changing runtime behavior and breaking people's CI builds. You know, and we're like, Rust's community is also just very heavily committed to, we'll never break a dependent CI build, which not all communities have that same level of commitment. And that too is sort of a double-edged sword. It has a nice advantage that allows us to do incremental package updates pretty much automatically, right? So if you ship some bug fixes and you say that they're Semver compatible patch versions, then everyone can just pick that up and if there's sort of this guarantee that it won't break anything, and that if it does, that's because they made a big mistake. And so because we like to have that guarantee, we also just consider a lot of things to be breaking changes.
I think one of the other big, and Eliza kind of touched on this in there, is that the Rust ecosystem gives you borrow checking. Part of the memory safety guarantees it gives you is this kind of static analysis of who owns what piece of memory, where in other languages like JavaScript, that's all garbage collection, right? And that is like the intersection of borrow checking and async is really where a lot of the magic is, but it's where a lot of the friction is in migration too.
Yeah. So there's a whole thing I could get into there if you really want to learn about the deep, deep stuff. Ask me about stack pinning sometime. But yeah, what Oliver's saying is it's a pretty deep fundamental change.
That's really awesome. Now I am going to need to go read a bunch about that because it sounds like something super awesome. As a summary, Rust introduced async await, which is awesome. And anyone who's worked with promises, futures, or callbacks realizes how much life is better with async await.
And in Rust, it's kind of especially painful in many cases to use the old promises or futures interface.
I totally can imagine.
For Rust reasons that we don't have to get into.
So that got introduced, which means that Tokyo, which is the kind of underlying async library for Rust,
right,
and the underlying async library for the proxy, it's going to update its APIs. And since we're doing it, they're breaking changes, we might as well do it all at once, so on and so forth. So that's kind of where we got to so far. What's the impact on the proxy now? And more importantly, could you tell us a little bit about all of those proxy PRs that I've been seeing?
Yeah, I would love to. So what's the impact on the proxy? Right now, there is no impact on the proxy because the proxy, I mean, there's no impact on the proxy that is on gcr.io, the proxy that is published with all of the like Linkerd releases. There's no impact on any actual running proxy in anyone's cluster because these changes have not made it back to master yet. What will the impact be? The biggest thing is that we hope that the proxy code base should be a lot more accessible and easier to contribute to. The old futures interface results in a lot of complexity. The new async await interface is in many ways much easier to work with, much easier to reason about, and you can write this sort of very nice straight line code instead of these sort of very complex manual state machines that you kind of have to write in the old interface that make the proxy code base pretty confusing, especially for new contributors. So it should be at least a little easier for newcomers or people who have contributed a lot to the Linkerd control plane, but not to the proxy and want to make some proxy changes to be able to read that code and, more importantly, to contribute to that code. That's maybe the biggest number one change. Number two change is that in the process of updating Tokyo to 0.2, we've rewritten a lot of the internals. We've made a lot of improvements in terms of efficiency and performance. So it's possible that once the proxy is fully updated to the new version, it might be somewhat to a lot faster. I know that
I'm going to put a big caveat in there, right? So
might be.
Yeah, the context there is that like we don't have to do a total overhaul of the proxy to start using these new libraries. And so the first step of this was to just use a compatibility layer and trying to use interop between the old world and new world. And what we saw was about a millisecond P50 hit in our benchmarks. And so we didn't want to roll forward with the compatibility shim.
Yeah, that's right.
The goal, like this, you know, we have to get this to a place where it all compiles again on the new code base, and then we're going to do more perf analysis to figure out
that's right.
We have this Linkerd proxy right now has a constraint on only having one core for the data plane, which for most folks is more than enough and helps us limit resource utilization. But for higher traffic scenarios can be a limiting factor. So after we get through this migration, moving to a multi-core proxy or allowing you to give the proxy more than one core will be
yeah, and that's absolutely right. And a lot of the projects that are using Tokyo's multi-threaded scheduler, which is what we would be using if we decided to move forward with adding, you know, the ability to run the proxy on arbitrary numbers of cores, have seen some, in many cases, really significant performance improvements since the Tokyo 0.1 version of the multi-threaded scheduler, even with the overhead of the compatibility layers. For the single-threaded scheduling, there is, which the proxy is currently using, there was a lot less room for improvement. Single-threaded scheduling is much simpler than multi-threaded scheduling, where we were able to make some really kind of fundamental changes in the scheduling algorithms that the proxy uses, or sorry, that Tokyo uses. My cat is still misbehaving. Sorry, I'm distracted by that. So there were some really like major gains that totally offset the overhead of compatibility layers. In the case of Linkerd, which uses the single-threaded scheduler, we did actually see the overhead of using the compatibility layers, partially because trying to do an incremental update involved putting compatibility layers in a lot of places. So we are trying to do the update atomically, or, you know, it's not atomically. We have a separate branch that's master-tokyo.0.2, right? That we're doing small PRs, mostly me, I'm doing small PRs against and merging them back incrementally and getting them reviewed piece by piece. Which is allowing us to more or less have our normal code review process, even though we're not merging anything back to master, because I've essentially commented out most of the proxy and now I'm sort of gradually uncommenting most of the proxy, right? So I am doing it incrementally, but not incrementally on master, because we did see a lot of overhead for those compatibility layers. However, once we are running exclusively on the new ecosystem without any of that compatibility overhead, we will definitely want to do a lot more performance testing, and then we might see some marginal improvements from the new implementations once we've factored out like all of the compatibility overhead. It's also worth noting that we cannot really do any benchmarking on the sort of in progress O2 proxy yet, because it wouldn't really be comparable, because as I said, I've kind of commented out most of what the proxy does. So we have this proxy that sort of has, it does TCP forwarding, and if you make an HTTP connection to it, it returns 200 OK. And probably by the end of the day, I'll have commented out enough, or uncommented enough additional code that it might sort of blindly forward HTTP traffic again. But it doesn't do all of the great things that Linkerd proxies actually do yet, because a lot of that code is still incrementally being updated. So we can't do a performance comparison with the current proxy because we're not doing any of the stuff that the current proxy does yet. Sorry, Thomas.
So, no, you're good. So I wanted to ask a question about that, because it makes me chuckle inside every time I think about this is how you're doing it. Not that it's wrong, I actually think it's awesome. Could you talk a little bit about what you mean by commenting out the code?
No, I mean, like, so something that's very cool about the proxy, here, I can actually show you. Can I screen share for a minute?
Yes.
Give me just a second, and I'm going to show you a cool Git diff. All right, so I'm just going to the proxy. I am going to my branch. And in just a minute, I will have this git diff to show everyone. And here we are. So I'm going to share my screen with you, if I can figure out how to do that. Sorry, I'm not a Zoom expert. Share, and I'm going to share Firefox.
Awesome.
So if we scroll just a little bit here, a lot of you who are Linkerd users probably know that we talk about Linkerd proxies as having an inbound and an outbound router. And here we have the inbound lib.rs, which is sort of, this is where most of the proxy's inbound router code is sort of defined. This is the top level definition. And what we can do is we see here, see on the left, we have, this is the previous, and this is the change. And you see here, we have this sort of big stack. We have an HTTP endpoint stack. We have an HTTP target observability stack that's layered on that. We have an HTTP profile route proxy, have all of this stuff, and we're sort of incrementally layering together all of this proxy behavior. And the really nice thing about this is that we've defined the proxy in a really modular way, where all of these different features or pieces of functionality that we want to do or behaviors are just layered together. And that gives us the power to, in many cases, do stuff like this, right? So here's my cool new proxy where, okay, I haven't updated any of this stuff to use the new Tokyo yet. I haven't updated like the HTTP target cache. I haven't updated any of the service profiles code, which you see right here. It's HTTP profile cache and so on. I haven't updated any of that stuff. All right, great. Let's just select all of this. And, you know, I use VS Code, so I just push Control/. Bam, it's all gone. The proxy still works. It took a couple changes. Here at the very bottom, I replaced the HTTP server with, oh, you can't see it because the Zoom chat is in the way. Okay, I replaced the HTTP server here with, now I have a server that just returns 200 okay, no body to everything. But, you know, so we can just take all of this and basically blow away all of the stuff that happens in the middle. And in a couple more PRs, we'll have both ends of the proxy, right? The accepting incoming connections and the connecting to a destination, right? And forwarding that traffic through a proxy that does no behavior. And it's not, it's nice that this implementation, and this is something that Oliver has put a lot of thought into, a lot of work into refining a really nice abstraction for building the proxy in a totally modular component-based way. And some of that is also something we've pushed into libraries that other Rust projects can use to do similar things.
So that sounds a lot like middleware for my Express server, for example.
Yeah, it's essentially, so we have this set of libraries called Tower that we've done a lot of work on, and Tower is essentially an abstraction for network services in Rust that provides a model for middleware. It has sort of an abstraction for like, here's how I write a server and a client, okay, and then here is the interface that I have to fulfill to have a middleware layer that wraps a service or a client and adds some behavior. And that's something that Buoyant has done a lot of work on. It's heavily inspired by Finagle. Finagle is a Scala library that is very similar. It's a sort of functional programming inspired RPC abstraction for defining these sort of middlewares and layers and services in a sort of functional programming inspired futures or promises based way They're called futures in Scala. And finagle, obviously, we use quite a lot in Linkerd E1. So Linkerd E1 is very finagle based. It sort of began its life as how do we take everything great that finagle did at Twitter and wrap it up in a proxy that we can ship to everyone. They don't have to use Scala. So this is in many ways trying to take the same model and make it work in Rust. And of course, it requires some, changes because the languages are different, and some changes to sort of refine some of the things that are a little too complicated or too confusing or whatever that we didn't like in finagle. But it's very, very similar. It's the same programming model. And
Awesome.
It essentially just defines a service as here's an asynchronous function, right, that takes a response, wow, I can't talk today. An asynchronous function that takes a request and returns a response. And once you have that definition, you can sort of compose functions the way that you would compose any function, right? You have a function that calls another function, great, that's function composition. You're doing functional programming, and so you can sort of layer middleware in that way. You can say, here's a function that has some other function that it calls, but before it calls that function, it does something to the request and then passes it on, right? So it adds a header, or it removes a header, or it, does whatever. Or you can say, here's a function that layers something on the response, and the response is asynchronous, right? So it's a future, or, again, a promise. So you have this function that, okay, here's a response that, right? Like I've taken some request, I've called some inner function with that request, and then I get this asynchronous future back, and I do something to that future, like, okay, I want to apply a timeout to it. If it takes too long to generate that response, right? And again, this is not a response yet, it's an asynchronous response, so it's a response that's coming. I want to apply a timeout to it, so I say, okay, if this takes this long, then we cancel it and we return an error instead, or, what have you. But you can layer this functionality on both sides of this request response paradigm, and most of Linkerd is written in that programming model.
Awesome. Okay, so I think this is actually a question for Oliver. We've got really cool work going on. When are we going to be able to see this in an edge? When can we start playing around with it?
Probably after 2.8. But the important thing is that you won't even know unless we do something wrong. There should be no user-facing impact unless it's yeah. But the goal is to not introduce any new bugs or feature changes or anything like that, just to do a straight port. So hopefully right after 2.8 we'll get that new edge.
If you notice that your proxies are consistently allocating slightly less heap memory across the board, we may have pushed it. That might be something that improves slightly. You're not going to notice. You will notice if you are making proxy contributions. So that's going to have a big impact on everyone writing Linkerd E2 proxy PRs. Hopefully it should make your life a lot easier.
Awesome.
I'm withholding judgment on whether it's easier or not, but we will see.
It'll be easier someday.
It'll be at least targeting what the rest of the ecosystem's doing.
Yeah, I guess Oliver brings up sort of the one other really big important reason for making this change, which is just that our dependencies are making this change. And because this interface is how we talk to pretty much all of our dependencies, it's really important that we are on the same version of the ecosystem as all of the libraries that we depend on, because it enables us to pick up all of their patches. And if they have already made this breaking change and they make patches that we want, and we're not yet on the new version, we have to sort of go and backport those changes. And that's a bit of a pain, and it takes time away from doing things that we would rather be doing. So making this change will allow us to continue just receiving all of the fixes and new features in the libraries that we depend on.
Awesome. Thank you so much, Eliza. That is a great deep dive. I really appreciate the time. It's always super fun to hear what's going on in the proxy.
Yeah, and that's what we're up to.
Cool. All right. So let me give you the next section we're moving into is RFC review. Let me give you a little bit of feedback or a little bit of a glimpse into what's going on there. We're trying to make it a little bit more transparent and easy to build out large functionality inside of Linkerd. And so about a month ago now, we introduced a process for proposing those changes. And so we've got a couple in flight, and I wanted to kind of call those out. I've got them in the links, or in the notes, but if anyone's interested, I will drop them in the chat as well. The first one we're going to talk about is the metrics API. Oliver, you want to chat for 30 seconds about what's going on there?
Yeah, we're talking to a number of issues coming up, both around new features we're developing, as well as some of the existing metrics we export. And we've had some plans in the long term around doing kind of RBAC and view isolation on metrics, and we wanted to just get our arms around that whole space and figure out what our roadmap is there. I think the result is that we're going to delete some code, focus on Prometheus as our kind of standard model for that, and lean on what Prometheus does for all those problems. And we'll publish a schema of labels that we promise to not break. And hopefully it's as simple as that, but we're still digging into the design, and especially the problem statement. So one of the big things with the RFCs is that we want to get really articulate about what problems we're solving and not just implement features because we're engineers who like to build features.
Amen to that. So kind of as an action item, anyone who's using the Linkerd metrics, it's super duper helpful for us for you to jump into the RFC and kind of comment on how it's going and what you think and whether those are problems you have and whether we're solving something that's important to you. So if you care about metrics, that's the right place to go and take a read and tell us what you think.
And right now it's just really the problem statement and some of the design sketch, but we'll be moving deeper into the proposal in the next week or so.
Yep, cool. And then the next one on my list is context sharing.
So context sharing actually came out of the discussion that triggered this metrics RFC. And so right now, when we give you edges and we show you traffic between data, that's always measured on the client side. We never really get high granularity data in terms of metadata on the server side, on the inbound side of the proxy. So the goal for context sharing is to start figuring out the mechanism that we can start sharing that metadata on connections between proxies. This also has some potential to allow us to do things like doing Mpls for server-speak service protocols. And so we're using, there are a couple of features that we may be able to satisfy as we think through the RFC.
Cool. Yeah, this is one I'm really excited about. Both the TCP MTLS or server speaks first protocol MTLS and some potentials on getting more data for metrics are exciting to me. That said, moving on to the next RFC, I'm not going to lie, this is my favorite RFC that we've done, which may seem simple to folks, but it's bring your own Prometheus. And
that dovetails with the metrics conversation again.
Yep. And specifically for bring your own Prometheus, while I still would recommend for most folks to run the Linkerd Prometheus and do aggregation, it produces more stability in your system. And the rest of that, there are some, I'm going to call them web scale users of Linkerd whose Promethei are just way too large to scale through anything that we can do. And so BYOP is all about giving folks the tools to change and figure out how they want to store their metrics.
Right, and I think we want to support both kind of, alternate federated Prometheuses as well as kind of leaning into folks who are doing things the Prometheus way and running independent Prometheus instances for each team. And so these two RFCs are kind of our way to think through that part of the problem.
Cool. Okay, on to Lincolni Heroes. I have a Linkerd Hero in mind. but I'm gonna ask you first, Oliver.
Good, I might steal yours.
No! This is backfired.
My Lincolni hero this month is Tarun. So Tarun's been doing, well, first of all, he just joined Buoyant to work full-time on Linkerd, which we're super excited to have him become part of the team there. And he's been working on RFCs. We've got through making Grafana an optional component, so you can disable edit install time and we won't link it in the dashboard. He added Jaeger links into the dashboard. These are all PRs that have come up in the last week, I think. So Tarun, if you're still on, good job. You've been kicking a bunch of butt.
The Jaeger links in particular is awesome. That's been the culmination of, I don't know, 4 months of work, 5 months of work for something that seems easy, but we needed to go and spend so much time on the underlying infrastructure to get to that point that it finally landing is really, really fantastic. All right. My nomination is Nassim, who, along with asking us fantastic questions and doing a bunch of great help in Slack, has got a monster PR that it's just about ready to land that I am so excited about. It's a great chunk of functionality. It's something that we probably wouldn't have gotten to that I'm super excited to see. And like the PR conversation and back and forth has been great so far. So seriously, kudos, Nassim. It's really been awesome to see that and work with you on it.
Yeah, and we even made a small proxy change, and he's
fearless. Yeah, I coded in Rust.
Yeah.
No, just kidding. Thanks a lot to Alejandro, by the way, who's been like kind of holding my hand through the PR as well. So
yeah, Alejandro gets the like hero reviewer reward because he reviews everyone's code and gives great feedback on all of it. So
I totally agree. It feels like if you haven't spent a bunch of time doing code review, it's easy to assume that code review is just easy, but it is as difficult or maybe harder than actually writing the code to go and provide really good review feedback and get folks to think things through. And so I totally agree. The reviewers are the unsung heroes of the world. All right, man, we're doing time perfect today. It is now Q&A time and or Stump the Maintainer. Does anyone have any questions about anything at all that they'd like to ask us about?
What's NF contract and why do you hate it?
Damn it!
This is why you get the hero award.
So here's all of the details. So NF contract is how the kernel keeps track of connections. It is used by Iptables, for example, to know where it's done its redirects, which is awesome. By default, it has a timeout setting of 60 seconds. What that means is if you have a request that takes more than 60 seconds, with the Linkerd proxy, by default, Iptables will drop the connection on the ground. It just doesn't know where to forward it anymore. It's lost track of the data. And so my dislike is at the moment because of Kubernetes interactions with some other NF contract details. Some folks that have requests over 60 seconds run into quite a bit of weird behavior where it looks like you just lost the request and no idea what's going on. And it is almost impossible to debug without going and doing some contract plus TCP dump.
I see TLDR requests that last longer than 60 seconds, watch out.
Pretty much. If you're on GKE, they've already set it to 3,600 seconds. There's actually
so one, it's not just requests, right? Any connection that's idle for this amount of time can get lost. Two, there are some things that we can and will continue to do in the proxy to like reduce this. So we can do health checks on the H2, we can do pings and things like that. And so some of those things are in flight and hyper and we'll be able to take advantage of. But yeah, just the complexities in determining where these problems are when it's the like host operating system just killing connections is like almost impossible to debug, like really, really hard. So that's why we did it.
And we're investigating if we can just make it 3,600 seconds by default for everyone. And so we're kind of on top of it. We're trying to look into it. It's just been, I spent maybe a month helping folks out in Linkerd Slack where I blamed DNS all the time, because in my defense, AWS DNS was busted for a bunch of reasons. But the last month for me has been suggesting that everyone's NF contract is wrong. And so that's kind of the summary there for me on NF contract.
Any other good questions or desired rants?
I could follow up with a quick one. Today we're running a monolithic cluster. Everything's in one cluster for reasons not important. We might create a second cluster and slowly move workloads to it. There are obviously two ways for clusters, for workloads in the original cluster to talk to the new one, and those two obvious ways are Linkerd multi-cluster service mirroring or just internal load balancer. I'm kind of, without having dug too deep, why would I choose one over the other?
So I like, if you care to do things like traffic splitting or using any of the SMI functionality to routing there, you'll want to use the Linkerd based solution because it, will be on the clients doing all that work. Also for MTLSing these things, the goal for multi-cluster is that you can create a single identity mesh, right? So that everything can MTLS to at least the gateways. And with getting, you won't have end-to-end authorization. Like we won't know the identity of the caller right now, but you'll know it's this gateway that I can call. So it's really around the kind of routing and security model. That said, there are good use cases for doing, ingresses for yourself. But the goal for our multi-cluster is basically to automate that ingress process for these use cases.
Thanks.
Cool, good question. Yeah, multi-cluster stuff's really interesting. It's funny because my background, especially at Twitter, was like one monolithic cluster and another monolithic cluster, and the two never talk to each other basically. And so seeing these like very, very hybrid small cluster environments come up has been fascinating.
Oliver, Charles just dropped a question into chat for you. I see that the roadmap includes work to encrypt TCP traffic. How is encrypting TCP traffic different than encrypting HTTP traffic?
Good question. So when we route HTTP traffic, we look at the host name or the authority header for HTTP2 and do routing based on that. And so if you call foo.bar.service.cluster.local, we go to the control plane and we say, oh, it's the foo service in the bar namespace. I can grab a bunch of metadata about that, give it back to the proxy. With that metadata is all the endpoints and their identities. An important thing to understand in the Kubernetes model is that we tie identities to the pod resources, not to the service resource. So a service does not have a single identity. It can map over pods that have multiple identities. And so all of that kind of feeds into our HTTP load balancer. The problem with doing TCP is that you are either calling a service IP that Coup proxy is going to route to a pod, or you're calling the pod itself. In the case where you're calling it the pod itself, it's fairly easier to do that, but that's a pretty rare situation in Kubernetes, since that would mean that you're basically doing your own load balancing and service discovery in your app. So most folks just talk to the Coup proxy API. We can't have an identity for the service. We can only have it for a specific pod. And we don't know what pod we're going to route to because Coup proxy is implemented in Iptables, which is beneath us. So what we have to do in order to implement MTLS for arbitrary connections is to do discovery of IP addresses for TCP and then do load balancing for TCP, right? And so we have to break this Coup proxy IP address into these 10 pods, and then we have to choose which pod to connect to and do the TLS to each of those individually. So we have a branch that kind of prototyped a bunch of this, and then we started focusing on the 2.7.1 stability work. At this point, I think the Tokyo migration becomes a big critical thing that we want to do before we move the MTLS roadmap forward, just because we're getting to the point where we can't upgrade certain critical dependencies. But yeah, it's like the next top priority after we unblock those things.
In fact, we're going to have an RFC up on that. I'm not going to give anyone a date, but
no, we have a
trademark
problem statement up there, and the design sketch will move forward. But I've prioritized other things that are actionable right now, where the MTLS stuff is kind of blocked in other work.
Yep. So if you're interested in this functionality, make sure to go subscribe to the RFC repo so that you can kind of see what's going on there and jump in and help out. And with that, I think we are out of time. Thank you, everybody, for attending. Really appreciate it. All the great questions. And we will catch everybody next month. Have a great rest of your day.
See you on the flippy floppy, as they say.